Hello, everybody. I hope you're doing well. Welcome back to another video reviewing your probability and statistics fundamentals. So in this video, we're going to be continuing our derivation of linear least squares. So just to make sure we recall the details from the previous video, the optimization we want to solve is this. So we have I equals 1 to n, where n is the number of data points. And we want to basically minimize the sum of square differences. So we want to minimize this value here, right? And we also know that y hat, which is a predicted value from our least squares line, is going to be mx of I plus b, right? Because every line has the form at y equals mx plus b. So that's just a refresher on what we've talked about. So what we're going to do is figure out how to find the optimal values of the slope and the y-intercept that minimize this expression right here. This expression is the whole reason why least squares gets its name from, because we're trying to do a minimization, and also we are minimizing the sum of the square differences. So the squares aspect in least squares comes from this idea of taking square differences between the predicted value versus the actual y value when we are fitting our line to the data set. And the minimization comes from the aspect that we're trying to minimize the sum. So that's just a brief recap on what we've talked about. If you're still confused on how we got to this optimization problem, I'd highly recommend reviewing the previous video where I explained how we come up with this evaluation metric. But let's proceed further and actually solve this. So what do we have here, right? So we start with I equals 1 to n. We're summing over our data points, and we're taking y hat minus y squared. Now, we know that y hat is equal to mx plus b, right? So this is equivalent to taking the sum for each data point from I equals 1 to n, because there's n data points. Data points are of the form x1, y1, x2, y2, and all the way to xn, yn, right? So these are our ordered pairs that we're going to fit a line to, right? So this expression here, we substitute our definition for y hat. So this will be mx of I plus b minus y whole squared. So we want to minimize this expression here, right? But how do we find the optimal values of m and b? Well, if you recall from our calculus class, if we want to find maximas and minimas, we use the derivative. And through the derivative, we're able to measure the rate of change. And by finding where the rate of change equals 0, or where the derivative equals 0, we are able to find minimas and maximas. So what we're going to do is take the partial derivative of this expression here with respect to both m and b to find the optimal values of m and b. What I'm going to do is start with taking the partial derivative with respect to b. If you're familiar with how to do derivatives of single variable functions, so like for example, f prime of, so if you had, say, f of x equals x squared, we have that f prime of x equals 2x by the power rule. If you're unfamiliar with the word partial derivative, basically what happens is when we take the derivative of this summation with respect to, say, m, we treat b as a constant. And we treat this guy as a constant too. Oh, never mind. We actually take, yeah. So when we take the partial derivative of a function with respect to a variable, we treat that variable as the single variable of interest and the other variables as constants. So we don't care about those. And we still proceed through our chain rule and product rule and all those rules that you learn in calculus. So let's first take the partial derivative of this summation with respect to b. So I will call this function e, and e is going to represent the error, basically. It's going to represent our objective, right? So we want to take the partial derivative of e with respect to b. So what will that be? Well, what we want to note is what the summation actually is, right? So what we're going to observe is that we're going to take the partial derivative with respect to the expanded version of this sum. Well, this is going to be mx1 plus b minus y whole squared plus mx2 plus b minus y whole squared, and so on up to n, right? And when we are taking derivatives of sums, we can take the sum of the individual derivatives. So since we have like this term here, and this term right here, what we can do is take the partial with respect to this term, and then, or take the partial of this term with respect to b, take the partial derivative of this term with respect to b, take the partial derivative of this term with respect to b, and then add those results together. So what we'll see here is that in this term, for example, right, the partial derivative will become, by the chain rule, right, we work on the outside, so you'll have 2 mx1 plus b minus y. And now we have to differentiate this inside part of mx1 plus b minus y with respect to b, right? But the thing is, m is a constant, x1 is a constant, y is going to be a constant. And actually, I forgot to jot down something in my sum. You'll actually subtract y sub I, right? We want to subtract the corresponding y value. So I want to make sure you are aware of that. So small typo here. And then this guy will become you will have a y sub 1 here, right? And you'll have y sub 2, and then you'll have y sub n. Okay, so now we want to take the partial of this expression here with respect to b. So you, by the power rule or the chain rule, you're going to bring the 2 down, and then now you have 2 times mx1 plus b minus y1. And then you'll see that since we're taking the partial derivative with respect to b, the m is a constant, the x1 is a constant, the y1 is a constant, but b is not a constant. So the derivative of b with respect to b is just 1 by the chain rule. And then likewise for this term, this will be 2 times mx2 plus b minus y2, and then we're going to multiply by 1. And then it's going to be the same effect for this term, right? So we can express this partial derivative as the following summation. So we're going to sum from I equals 1 to n, and it's going to be 2 times m x sub I, so it's that specific data point or order pair we care about, plus b minus y sub I multiplied by 1. So this is the partial derivative of e with respect to b. Now what we're going to do is we still have to solve for this partial derivative equaling 0, right? But what I'm going to do is actually expand out the sum, right? So by summation properties, this sum is equivalent to taking the sum from I equals 1 to n of 2 m x sub I plus 2b minus 2 times y sub I. And then since we're taking the sum of terms that are summed in, we can actually separate out the summations. So this will be I equals 1 to n of 2m x sub I. So let me just make this a little neater. Plus summation from I equals 1 to n of 2b minus summation from I equals 1 to n of 2y sub I, and this is going to equal 0. Now what do we notice? When we have constant multipliers and sums, we can actually pull out the constant multipliers. So this 2m is a constant multiplier, so we can pull this out. The 2b is a constant as a whole, so we can pull it out. And then this 2 here is a constant, so we're going to pull it out. So what we'll have is this is going to be 2m summation from I equals 1 to n of x sub I plus 2b summation from I equals 1 to n of 1 minus 2 times the summation from I equals 1 to n of y sub I. And now this is going to equal 0. Now what do we notice here? Well, we know that 2b times the summation from 1 to n is just going to be 2bn, right? Because when we're summing 1 from 1 to n, it's just going to be adding 1 to itself n times, which is why the summation from I equals 1 to n of 1 is just n. So now what do we have here? This is going to be 2m summation of I equals 1 to n of x sub I plus 2bn minus 2 times the summation of I equals 1 to n of y sub I, and that's going to equal 0. Now what's left is to solve for b, so we're just going to use some algebra. So what we'll do is we can move this term here and this term here to the other side, basically. So what that will give us is 2 times the summation from I equals 1 to n of y sub I minus 2m summation from I equals 1 to n of x sub I, and this is going to equal to 2bn. So we're going to divide by 2n on both sides. And what will that give us? Well, that will give us 1 over n times the summation from I equals 1 to n of y sub I minus m over n times the summation from I equals 1 to n of x sub I. We're almost done with solving for b. We still need to recognize one more pattern. So when we're summing all the y values and then dividing by n, what is that equivalent to? Well, that's equivalent to taking the average. So this is actually y bar, right? It's just the mean, basically. And likewise, we notice that here we're taking the sum from 1 to n of x sub I. So we're summing up all our x's in the data set and then dividing by n. Well, that's equivalent to taking the mean of all the x's. So this is m times x bar. So basically, we have found that b, let me have this, erase this. So we have found that b equals y bar minus m times x bar, where m is your slope, y bar is the mean of the y values, and x bar is the mean of the x values. So now that we've solved for b, we're going to use that to solve for m. So again, we're going to take the partial derivative of our error function with respect to m. And as you may recall, right, this is the error function here we're trying to optimize. Let me box this in red. So we want to optimize this function, right? So we want to take the partial derivative of this function here, which is equal to e, with respect to m now. So now what we're going to do is proceed in a similar fashion, right? So this is going to be equal to the partial derivative of e with respect to m. And this is going to be we're going to expand out the summation, so we'll see a pattern. So this will be mx1 plus b minus y sub 1 squared plus mx2 plus b minus y2 squared plus all the way to mxn plus b minus y sub n squared, right? And now since we're taking the partial derivative of a sum, we can just take the partial derivatives of these individual terms and add up the results. So what do we notice here? The partial derivative of this term here with respect to m, well, we use our power rule, right? First, because we have to use the chain rule. We work from outside to inside. So this is going to be 2 times mx1 plus b minus y1. And then now we have to multiply this inside expression and with the derivative with respect to m, right? So when we're taking the derivative of mx1 plus b minus y1, we notice here that the only term that m affects is the mx1 term. This b and this y1 term are constants. So we take the derivative of mx1 with respect to m, right? Well, that's just simply x1, right? And then likewise, this derivative will become 2 times mx2 plus b minus y2 times x2. And you might guess that there is a pattern in how we're constructing these partial derivatives. We can actually sum this up, and we can write this in a compact form. We're going to sum from I equals 1 to n, and you'll notice that here, in these partial derivatives, for these respective terms, the x1s here and the x2s here correspond to what x value we're talking about. So we can compact this representation into a sigma notation, and that's going to be 2 times m x sub I plus b minus y sub I times x sub I. Okay, so now we have the partial derivative of the error function with respect to m, but we still have to do something. We've already solved for b, which was through here. Let me box the solution here in red. So we have solved for b right here. What we're going to do is substitute the value of b, which is y bar minus mx bar, right in here, right? So when we substitute, what do we get? Well, this is going to be equal to the summation from I equals 1 to n of 2 times m x sub I plus y bar minus m x bar minus y sub I times x sub I. And then what we're going to do is we're going to group the terms with an m together, and the other terms are going to go into another summation. But what we'll do is distribute this x sub I over all these terms. So this is going to be summation from I equals 1 to n of 2 times m xi squared minus m x bar x sub I plus y bar x sub I plus x sub minus this will become a minus y sub I x sub I. And then now what we'll do is expand this sum out. So this will be I equals 1 to n of 2 times m x sub I squared minus m x bar x sub I plus summation from I equals 1 to n of 2 y bar x sub I minus y sub I x sub I. And then now we set this partial derivative equal to 0. Well, what do we notice here? We have a constant multiplier of 2, right, in both these summations that get pulled out as a common factor. But since 0 divided by 2 is 0, we don't care about these constant multipliers. They don't really matter, right, in the grand scheme of the optimization problem, right? So now what we'll do is we can then expand out this sum to find something for m, right? We want to make m isolated so that we can solve for it. So this will be m times the summation from I equals 1 to n of x sub I squared minus x bar x sub I. And what we're doing here is we're recognizing that the m is a constant in the grand scheme of the summation, so we can essentially pull it out. So that's why we're doing this. And then in this term, we don't really have to do anything here. I don't think there's anything really necessary to pull out. I mean, yeah, there's really nothing necessary to pull out other than the fact that we can pull out this y sub I. Like, we can pull out this y bar I meant in this term. So I can actually expand that out and do that. Since y bar is a constant because the mean is always a number, we'll pull it out. So we'll have plus y bar summation from I equals 1 to n of x sub I minus summation from I equals 1 to n of x sub I y sub I. And that's going to be equal to 0. So now what we have left is to solve for m, basically. So we're going to bring these terms here in green to the right-hand side, and then we're going to divide by this summation, and that should give us the answer that we need. So here's what we're going to do. So the result is going to be this. So we have m times the summation from I equals 1 to n of x sub I squared minus x bar x sub I plus, this is actually going to be set equal to summation from I equals 1 to n of xi yi minus y bar summation from I equals 1 to n of x sub I. Okay, now what's left is we're going to divide out this summation here in green, and that'll give us an expression for m. So we're going to divide by the thing in green, so this will be divided by I equals 1 to n of x sub I squared minus x bar x sub I. And then we're going to do that on this side. And now, from what we got here, we have the following for m. So m is going to be equal to this expression here, right? Summation from I equals 1 to n of x sub I, y sub I, minus y bar, summation from I equals 1 to n of x sub I. So I'll put this terms here in parentheses to be clear. And then we're going to divide by summation from I equals 1 to n of x sub I squared minus x bar x sub I. And this is our formula for finding the optimal value of the slope. So what do we notice here? We have found our value for the optimal value of the y-intercept of the line. And right here, we've derived an expression for the optimal value of the slope. The only thing that you'll notice that's different between these equations and what I've derived is that this equation for m can go through several other conversions to establish the equivalence between this expression here and this expression here as shown at the top. It's just that you'll see in books that the expression for the optimal slope is going to be written this way, and the optimal y-intercept is going to be written this way. But if you do some conversion, or further manipulation from this equation to this equation right here, you will be able to derive an equivalence and eventually come to the conclusion for the optimal value of the slope for the line of best fits. So yeah, we have solved the minimization problem, and what we'll do is we will be able to use these equations to be able to further evaluate how good our line of best fit is. So until next time, I will catch you later, but if you have any questions, feel free to drop a post in the comments, and I look forward to seeing you later. Thank you everyone, and have a good rest of your night.